Welcome Science 10 to our next lesson on 3.4, the mole. Not this kind of mole, not this kind of mole, but instead the mole we're talking about is the amount of a substance. So when we're looking at really tiny particles, as in the particles of elements, we have to use a very large number when we talk about reactions with them because the particles are so tiny. So just like we might call a dozen eggs, knowingly that there's 12 eggs, we might say that there's a mole of a substance, and we know that that is specifically 6.02 times 10 to the 23rd of those particles. It's a very big amount. And how we chose that number, it's called Avogadro's number. It was chosen because it's exactly how many particles would be in 12 grams of carbon 12. And for some reason, they used carbon as the one that they were going to compare all others to. And when you're thinking about any particular formula, like the fact that 2 molecules of water are broken into 2 molecules of hydrogen and 1 molecule of oxygen, this is a balanced chemical equation. You could also say this in terms of 2 moles of water can be broken down into 2 moles of hydrogen and 1 mole of oxygen. So sometimes that coefficient put in front is also referred to as how many moles of those substances are going to be in a balanced equation. Moles are so tiny. We know a dozen is 12, but moles, if you watch the little video that was in the clip in the beginning of this PowerPoint, or if you read through the green pea analogy, thinking of green peas, you guys can read through this, but basically to imagine how many that mole is, you can think about taking 250 planets the size of Earth, covering them with a blanket of peas a meter deep, and that would be how many a mole is. So it's a very, very, very large number. And what you can see on the periodic table, if I can just go down to my bookmarked table, is that for any element on the periodic table, there is a molar mass right there on the right side of your periodic table box for each element, and that is the molar mass. That is how many grams you would need to get 1 mole of that element. So it would be 65 and a bit grams to get 1 mole of zinc. It would be 26, almost 27 grams of aluminum to be a mole of aluminum. It would be just over 24 grams of magnesium to be a mole of magnesium. So those are the molar masses that are shown on the periodic table. And we'll be going back to that again later and talking about how we can use that in doing some calculations. So going back to the fact that as the elements were organized on the periodic table, they were all organized in increasing molar masses. So their masses all the way up the periodic table get higher and higher, and that's how they were organized. Okay, going back to my bookmark, I was going to also point out that the carbon that we're comparing it to is an actual 12, as we were mentioning earlier. Okay, and I think we're on this slide here. And what we have to do in today's lesson is just look at how we get a molar mass of a compound. So to get a molar mass of an element, 1 atom of an element, you just look at the periodic table and check out that molar mass. If it's a compound though, like carbon dioxide that's in this example, you actually have to go to your periodic table and add them up. Add up the molar mass of carbon, which we saw was 12.01, and you have to go 2 times the oxygen to add those all up in this molecule of carbon dioxide, because there are 2 oxygens. So oxygen being 16, as you can find on your periodic table, you'd have to go 2 times that, and as you add them up, you're going to take 12.02 and the 32, and that adds up to 44.01. This is not hard to do. You guys will find it very easy to add the components of any formula together, but you do have to do that practicing, as we'll talk about. If your notes are open, page 29 has practicing that you can do for adding up the amounts of molar masses in any compound, whether it's ionic or molecular compound. These are all really easy to do. This correct formula here, it just didn't show up very good on my screen here, but it's Na2CO3. And to get the molar mass of sodium carbonate, you can see we need 2 sodiums, so we just multiply the 22.99 that we find sodium is, and again, I can point that out in here, that we're getting it from the molar mass right on the periodic table for sodium. And so we have to go 2 sodiums, which will be 45.98. We have 1 carbon, which is 12.01, and we have 3 oxygens in this molecule. So we have to go 3 times 16 for a total of 48. When you add the 3 of these together, it's 105.99 grams per mole, and that would be the molar mass of sodium carbonate. So what we want to do now is go to your page 29 and add up some molar masses to practice this. And for that, I added this to my slide here, but on page 29, to do the first couple with you, and then you guys can try the rest of these examples. But for chlorine, the formula is Cl2. It's one of our diatomics in the shape of a flag, remember? So to get the molar mass of chlorine, you do have to go 2 times the 35.45 molar mass that you'll find in the periodic table. So it will end up being 70.90 grams per mole. You just add those components up. I can try number 4 with you, and what I like to go is say there's 1 magnesium here. Magnesium, you can look it up, is 24.31 grams per mole. When we have brackets, this does mean there's 2 oxygens, and 2 oxygens is 2 times 16, which is 32 grams per mole. There's also 2 hydrogens, and the 2 hydrogens, hydrogen is 1.01. 2 times that is 2.02, and as we add those up, we see that it's a total of 58.33 grams per mole, which is the molar mass of magnesium hydroxide. So it's really important, Science 10, to try these out. I will include the key on Google Classroom, so you can check those out. I want to go down to the bottom of page 29 and try one of these with you. The extra step in these is that they have some of them not listed with their correct formula. So something like sodium hypochlorite, you may have to get the formula before you can do the question. I guess I can do maybe sodium carbonate decahydrate with you as an example, and sodium carbonate, pardon me, is one we just did in the other page, so maybe I'll try a different one. I just realized that. Okay, how about we can try the Na2S2O3.5H2O together, number 10. And for this one, we see there's 2 sodiums, So 2 times the 22.99 would be 45.98. We also have 2 sulfurs. So 2 times 32.06 would be 64.1. So I don't know what that was. 64.12. And going on from there, there's 3 oxygens. So that would be 3 times 16, which is 48.00. And then whenever they have one of these hydrates, we have to remember that you can add up the parts of water all together, but it will add up to 18.02, 16 for the oxygen and 2.02 for the 2 hydrogens, and you do have to multiply that by 5. So 5 times the 1802 for water will end up being 90.10 grams per mole. And all you do is add all of those together, and the actual total here is 248.22 grams per mole. And you have a total for that molecular compound. I will give you a chance to try adding up as many of these as you can, add up the molar masses, and where this will be very important is because our next lesson will be on using the mole calculation, and you need to have the ability really down in adding up molar masses of any component or any molecule that the question is describing. So give these a try, and I will see you back for another lesson shortly.